Well, good afternoon, and I hope you guys all had a wonderful Thanksgiving. Chatted for a couple minutes with a few of you as we were getting started here today, and it's good to see you all. And we have just such a short amount of time leading into Christmas break. It's kind of hard to believe, but our exam is scheduled for 2 weeks from tomorrow. And actually, exams start not this Friday, but next Friday. So we are on the cusp of the end of the semester. It's hard to believe. And we've got to put up the agenda so you can see some reminders and what we're going to be covering today. So just very quickly, a reminder that the Positive Physics Unit 5 assessment is due tonight. So if you haven't turned that in yet on Axis, just make sure you take a picture that shows your name and then the original score and then the corrections score. There's a couple places you can do that. Just in the assessment itself, if you just take a snapshot of the upper corner, it shows your name and both percentages when you're done. Or you can take a picture of the dashboard and it does the same. But that's due tonight. And I'm going to try to save you at least 30 minutes. We had 30 in one class and 35 in the other. So hopefully at least 30 minutes for you to work on that in class today. Or if you're done, begin preparing for the final. Some ways that you can review as you're wrapping up the semester. Like we said, the exam's 2 weeks from tomorrow, our exam. You can be reviewing on the AP Classroom the first 2 units. By the end of next week, we'll have covered all of those 2 units. It's a little odd the way they divide it up. Really half of the course is in 2 units, and then they divide all the rest up into a bunch of smaller units. So, but you can review those 2 units. On Positive Physics, we'll have covered units 1 through 9 by the end of next week. And then unit 12 is actually going to be your final. So I'll explain that here in a couple minutes. As I've mentioned, the exam's next 2 weeks from Tuesday. And then we'll be taking some review notes today. Not too much new today, mostly just making sure you caught all the details from what we covered before break, refreshing your memory, getting you thinking back about physics again, and then adding just a few new examples and a few new ways to visualize. So that's why it's a fairly short lesson today. And then at the end, like I said, time for you to work on the Positive Physics, either Unit 5 assessment if you're not done yet, or preparing for the exam. So let me just go to the Positive Physics website and show you how your exam will work. And I'll just log in as a fake student here so you can see exactly what it'll look like for you. Right now, when you log in, it should take you right to Unit 5 because that's the one that's due today and tomorrow for B-Day classes. But the exam, if you look at the units, their set of units is divided up more like our flow. We've already covered 1 through 6 entirely. We've covered bits and pieces of 7. And then today we'll be starting to address 8 and 9. And those will also carry over into Thursday's lesson and the next Monday's lesson and the next Wednesday's lesson. Next week, it's Monday and Wednesday are A day, Tuesday and Thursday are B day, and then next Friday is actually the first exam day. So we'll have covered everything you should know from the first 9 units. We will not be covering 10 or 11. Those will be what we start with in second semester. And then Unit 12, you can see, is a forces and motion review. And that's what we're going to be using for your exam. Since we're not going to be on campus, we're just going to use the Positive Physics resource, which in some ways will make it easier for you than a traditional exam. The curve won't be as steep because it's easier, but you should still be able to score quite well. So if you go to Unit 12 on the Positive Physics site, you can see there's a lot of skills, a lot of sections, because it's trying to review all 11 units. You can see the first topic or skill is extrapolate. There's only 1 question there, but there's 18 vocab and 12 motion concepts and on and on and on. You can see all the way down, ending with some challenges. And it basically tries to go through all of the units, also with some additional subjects. The extra practice just sort of gives you a kind of a practice assessment. It randomly picks a certain number of questions from every category and then just gives you practice if you want to try that. But every question is in the work section. The assessment, you can see, has black little locks over here. It is still locked and I won't unlock it until we're ready to take the exam on that Tuesday, the 15th. But you can click on it to see how many questions there are from every topic. So in the extrapolate topic, I didn't choose that question at all. So it's 0 on the assessment. There are 4 vocab. If we go back to the work section, you can see there's 18 total. 4 of them are going to randomly be drawn from that collection onto your exam. 3 of them from motion concepts, 1 for motion charts, and on you can see. You can see down here at the bottom where it has motion, circular motion and universal gravitation. I've put 0 and 0 because those are the 2 topics we won't have covered yet. Those will be starting next semester with. But basically, when we're done with this semester, you'll have covered all the first 9 units and done unit 12 as your exam, leaving us 10 units to do second semester. So we're exactly halfway on the positive physics side. But if you look at this, you can count it up. There's 30 questions on the assessment. Again, you can't access the assessment right now, but you can go through the work section, and knowing that there is not a question on extrapolate, you could just skip that and go on into the other sections. Also, for instance, if you click on the vocab section on the assessment, there are only 4 and there are 18 there. But if you look at these 18, all the ones that are highlighted in purple, if you click them, it says this problem has been removed by your teacher and will not affect your score, meaning those ones in purple don't show up on the final. Okay, so as you're going through, while there's, I think, like 130 some questions on this unit, you don't have to do the circular motion part at all. You don't have to do the universal gravitation at all. You don't have to do the extrapolate at all. And any of these purple highlighted ones, you don't need to worry about as well. Now, it wouldn't be bad to review them because they could be questions you would be asked next semester, but in terms of content and topics, but they are not going to be on your exam this semester. So if you do spend the next couple weeks when you have time going through unit 12, you can be practicing in the work section and basically practicing your future exam questions. The thing that'll be different is the numbers will change and each student will get a random assortment. So every student's going to get 4 vocab, but Lily might get 4 different ones in Jackson and 4 different ones in Jenny. You guys kind of know how that works. I figured using the positive physics would be good since we won't be on campus. I think we've had enough technical difficulties with access that I'm not really willing to risk your final exam grade using that resource. This is something you should be fairly familiar with. You've done it a few times and you can do as much preparation as you want. I mean, this should be a pretty easy exam for you if you spend a lot of time going through unit 12. Now, you could also, for review, go through unit 6, 7, 8, and 9, but it's all going to be from 12. In fact, we'll just go to 12 and click on the assessment that day. The way it will be graded, it won't be curved in the normal sense, but the theme is still the same. Normally, you get the curve if you do the corrections. The way I'm going to grade your final is you'll have, it's I think 8:30 to 11:30, so it's a 3-hour time window. I'll open it at 8:30, and you can use as much of that 3 hours as you need. If you need an hour, that's fine. If you need 2 hours, it's fine. If you finish it, finalize it, and go back and make corrections, then I will average your corrections percent with your original percent as your exam grade. Okay, like we're doing on this unit 5. So it'd be the same process. So if you prepare well and you know how to do all those questions, when your 30 pop up, you should be able to crank through it, finalize it, go back and correct anything you missed, and I think hopefully do very well as long as you can spend some time between now and then preparing. And I won't be giving you very many assignments between now and then, because if you do this, you're actually reviewing all the things I want you to do, and you're reviewing forces, which is what we're studying. There might be a couple little, I may say, hey, do this one problem tonight or something, but primarily I want you to focus on this. So any questions? All right, so that should take some stress off the physics exam, at least for this semester, since you know very well how to prepare for it and what you can expect. When we take the exam, while I won't really be answering any questions during the exam, you can, if you're working on it ahead of time, ask questions. I'm going to try to give you around 30 minutes of work time every period that we have. So at the end during that work time, if you've had questions from positive physics, you can just stay online and say, hey, Mr. Webb, I'm working on the exam and I can't figure out this question. Can you help me? I'm more than happy to do that. All right. So we've talked about the exam. We've given you your reminders. Let's go ahead and jump into the notes for today and review forces and Newton's laws. So this is the PowerPoint actually from your textbook publisher. So if you haven't been reading through unit or chapter 4 and chapter 5, that's what we're covering. I'm going to try to get through most of the chapter 4 PowerPoint today. And then we're going to wrap that up and get through some of the chapter 5 PowerPoint on Thursday. And then next week, mainly just wrapping things up and practicing problems. So what we're talking about in units 4 and 5, or chapters 4 and 5 actually, is what does make an object accelerate. And this is what we started talking about before break, but want to refresh your memory, bring your mind back to physics, back to what we're talking about. If there is a single force exerting on an object, then that object will accelerate in the direction of the single force. Acceleration is meaning we're changing the velocity. And since velocity is a vector, maybe changing in magnitude, which would be the speed, or maybe changing in the direction. Either way, that's an acceleration. And that's an important concept. That's one that AP frequently tests you over, and positive physics as well, that you understand just changing the direction also would be a change in velocity, even if the speed stayed constant. And I've tested you over that already as well. The last thing here is if there is no net force exerted on an object, the object will not accelerate. Now, some students get a little confused by this phrase, if a single force exerted on an object, and they say, wait a minute, Mr. Webb, we've talked about Newton's third law. We know forces come in pairs. But when we talk about forces coming in pairs, that means we're talking about exactly two objects and how those two objects basically share a force pair between them. In this scenario, we're saying if a single force is exerted on an object. So in this concept, we're just focusing on one of those two objects and the force as that object experiences it. Okay, so it's not that Newton's third law doesn't work or that we're ignoring it, but when we're thinking about Newton's third law, we're not just thinking about one object, we're thinking about two objects at a time and the force pair that they share. When we draw a free body diagram, we choose one object and we focus in on just that one object. So we're not necessarily thinking about Newton's third law pairs when we're drawing free body diagrams, which is what we're going to start with. We will finish with Newton's third law at the end of today's lesson. But if that's been confusing to you as to why we don't always think about the pairs, when we think about force pairs for Newton's third law, that means we're thinking about two objects at once. And so again, we'll review that later today. So here's just the restating of that same thing from the previous slide, but here is a follow-up statement from that. If there are more than one force on that single object, if there are multiple forces affecting that object, we can replace them with a single force. So kind of like we did with displacement and velocity before, we can use those two velocities or two displacements and triangulate it and create a resultant. We can do the same thing with forces. We can add them up as vectors and come up with a single value that represents all of those forces combined as vectors. We call that single replacement value the net force, and we can symbolize it as sigma F, showing that we're literally summing up all those vectors as forces, or we can call it F sub net, meaning it's, again, a net force. So just reminding you about that concept of net force from prior to break. Now, with the different kinds of forces that we've learned about, we'll review some of those briefly here. If I have a ball hanging from a rope, then we could think about the force pair there as Newton's third law. There's the ball and the rope, two objects. So the ball exerts a force on the rope, and the rope exerts an equal and opposite force on the ball. That's how we think through Newton's third law. If we were just thinking about the ball, however, we would say, well, the ball as one object is experiencing gravity pulling it down, and then the tension in the rope pulling it up. So when we focus in on one object, we're not really thinking about those force pairs. We're just thinking about the forces that act on that single object. If we think about a person pulling on a rope that's attached to a wall, the person's pulling on the rope, and then the rope is going to have tension as a result of that. So the person is exerting a force on the rope and the wall is exerting a force on the rope. So we really have three different objects we're considering. If we made the rope the object of focus in our free body diagram, we would have the wall exerting a force and the person exerting a force in opposite directions. Some other examples of just forces and how we might name them. If we see a tug of war, we've got different people pulling in different directions and creating a tension force in the rope. If we think about an object just at rest or in motion, but thinking about its weight, like this car we can see, it has weight due to the gravitational force field of the Earth, And because it's not falling into the earth or being drawn down to the center of the earth must be providing a normal force supporting it. And then we call that weight, we call that F sub g weight, or you can call it gravitational force. We will focus on gravitational force as weight, but there's another way to think about gravitational force as the attraction between two objects that have mass. And we're going to save that aspect of gravitational force till after the exam and after this semester. So we will only focus on gravitational force for now as weight. The gravity between two objects will wait till after Christmas. The idea of replacing multiple forces with one and coming up with that net force is something I want to illustrate here with several examples. If we had this object, whatever this green box represents, it has a force to the left that's small because it has a small arrow, and a force to the right that's large because it has a large arrow. Therefore, the net force would be that rightward positive large force minus that leftward force, which you could either say we're subtracting it or you could say we're adding it as a negative since it's in the leftward direction. The net would be the leftover. Some of that little leftward force cancels some of the effect of the rightward force. So the net is what's left over when we cancel out those portions. And whatever direction the net force is pointing in, that is also the direction of the acceleration. And we mentioned that before the break, and it's going to come up 6 or 8 times on the slides today. They're trying to really hammer home that fact that once you've identified the direction of the net force, that direction is also the direction of the acceleration. So this would have a net force to the right and therefore would be accelerating to the right. If we had another scenario where that same object had two forces that were opposite but also equal in magnitude, they would entirely cancel each other out, and that net force then would be 0. Since the net force is 0, there is no acceleration. Now, one of the things that sometimes students will get mixed up on, though, just because it's not accelerating doesn't mean it's not moving. Okay, it could very well be moving at a constant velocity. It just isn't speeding up, slowing down, or changing direction. So 0 net force means no acceleration. Doesn't mean necessarily no movement. If we look at our next example, we've got two forces both acting to the left. So we could add those up as vectors, saying that the net force would be to the left, and therefore it would accelerate to the left at the sum of those two forces. We could even look at a more two-dimensional concept where we've got forces both in the vertical plane and in the horizontal plane. And we do need to separate the horizontal and the vertical when we are looking at forces, just like we did velocities and displacements for projectile motion. So here you can see we've got two vertical forces, one up and one down. Those are equal and opposite, so they cancel. We have two forces left and right. So horizontally, those also cancel. So in this scenario, we have a total force or net force of 0, meaning this object will not accelerate. It will either stay at rest or it will continue to move at its already existing velocity in the same direction and at the same magnitude. And then the last example for this part, if we have an upward force and a leftward force, since we have to kind of separate the two, but there's only one of each, the only way we can combine them is to use that whole triangulation process we did with velocities and displacements. We can, even though they're not components, they're actual forces, we can treat them like we treated components of velocities or like we could treat components of a force. But in this case, the actual forces are the two red arrows, and the blue is not really a force, it's just the net result of those two. If we know the upward red force and the sideways red force, we can just use Pythagorean theorem. If it's a right angle, it's vertical and horizontal, and we can find the magnitude of that net force. Then we could use trig to find what angle it would accelerate in, because again, the direction of the net force will be the same as the direction of the acceleration. So just some examples on how we could combine a variety of different force combinations to determine the net force or determine that the net force is 0. Questions? All right, so to wrap it up, if the net force on an object, if there is a net force on an object, then the object will accelerate in the direction of that force. No net force means no acceleration. Having a net force means it will accelerate in that direction. Now, here is a concept that often gets tested and sometimes confused by students. Not the first part, that no net force means no acceleration, but the second part in red. Just because we know there's no net force and there's no acceleration, we don't from that information know anything about the velocity other than that it's not changing. We can't assume it starts at rest. We can't know what the direction or the magnitude of the velocity is actually. Could I get someone to unmute and read what's in this box on the upper right?
I can.
Thanks, Jeff.
The object has zero acceleration because there is zero net force. Therefore, the object has constant velocity. The object could be moving downward with constant velocity or to the left with a constant velocity, or it has an unknown constant velocity in an unknown direction, or it could be stationary. Yeah.
So that whole or ... basically they're saying we could go on and on. Like we could list all kinds of scenarios, but in the end, all we know is the velocity is not changing. We don't know the direction. We don't know the magnitude. It might even be at rest, but we can't assume that. And so the problem sometimes students will have is they'll assume it's at rest, even though maybe it isn't. So this is just to warn you against making those assumptions. If there, yeah, question.
I have a question really fast. So would an example of something moving but without acceleration but still having forces acted upon it would be like if something was, I remember there was a squirrel fall on a roof question on the last one. So if the squirrel was sliding off the roof, the weight, but like the friction was like counteracting its weight, so then it was just like staying at a constant velocity. Would that be an example of that?
Yeah, that would be.
Okay.
The other squirrel, I thought you were going to go with that squirrel, the flying squirrel that we did on another day, where we were saying it reaches terminal velocity because the drag force balances its own weight. And so in that case, it would keep falling, but it wouldn't be accelerating anymore. It just keep falling at that same speed.
Okay.
Yeah, so two examples there where that would be illustrated, where there's no net force and no acceleration, but still movement. If there is a net force, then there is an acceleration in the same direction. And so that's not too hard, but keep in mind again, we still don't know anything about the direction of the velocity. Just because it's accelerating that direction, maybe it's actually slowing it down. And so the velocity might be in the other direction. So we don't know the direction or the magnitude of the velocity just because we know the acceleration. We can't make assumptions. Could I get someone else to read this second big box on the right?
Yeah, I can read it.
Thanks, Gavin.
Yeah. The object is accelerating in the direction of the net force, therefore the object's velocity is changing. So however, we have no information about the size and direction of the velocity of the object at that instant shown in the picture. So the velocity is changing in the direction of the net force, but from what velocity, we have no idea. The picture doesn't give us that information.
So there will be some questions where they do say it's from rest, or they do give you some values, but if they don't give you any values, don't make any assumptions. Sometimes the answer is we can't know. There is not enough information given or something like that. So don't make assumptions that something is at rest or that something is moving in the direction of its acceleration. It's possible that it's moving in some other direction. So we can't make assumptions. And this is a nice slide to help remind you of those little things that sometimes College Board tries to trip you up with. Okay. Newton's second law. So now we're going to kind of quickly go through each of the laws. We'll spend the most time on second law, then first and third we'll go through pretty quick. So the second law is basically the relationship between how mass and force are related and how acceleration and force are related. And so we know mass is basically the inertia an object has. The more mass it has, the more inertia it has, the harder it is to get it to accelerate. And so we also talked about in our notes before, if you solve this for A, you can see how the acceleration is directly proportional to the force you apply, but inversely proportional to the mass of the object or the inertia of the object. And just a quick reminder of the units: force is in newtons, mass is in kilograms, acceleration is in meters per second squared. So you do have to make sure your units match this. Sometimes it's easy to make a mistake that way because you see newtons and then maybe they give you the mass in grams. It has to be kilograms to cancel with the newtons. So make sure that you're aware of those different units. And again, they keep emphasizing this point: whatever direction the force is in, the acceleration is in that same direction. So the net force direction and acceleration direction are identical. A couple other things about Newton's second law. If you're trying to think about how to define a Newton, you can think back as to how we calculate force. And that is we take the mass times acceleration. So it's kilograms times meters per second squared. So a way to define a Newton would be to say 1 Newton of force would be what's required to accelerate an object that has a mass of 1 kilogram by 1 meter per second squared. So just thinking of the units can help you identify the meaning of that term Newton, or that measurement Newton, that unit. The net force will always cause an acceleration in its own direction. So here's like time 4 or 5 that they're saying the same statement over again. But this is something new. Only external forces can cause acceleration. And this also sometimes confuses students. So if we're thinking about like a skater skating across a pond, we don't need to worry about their heart pumping or their muscles flexing. The skater becomes a dot, right? We don't think about the motor turning in a car or the passengers moving in a car. The car becomes a dot. Anything internal to the object we can ignore. We only think about the forces external to that object. It doesn't come up very often, but every once in a while they try to trip you up with a little sneaky thing where they give you some unimportant information and makes you think it's important. If it's internal to the system, it is not important. And then the last, this is just a review of Newton's first law, really. Mass is a measure of the inertia. Inertia is the unwillingness or resistance of an object to accelerate. Unwillingness seems kind of like an odd word to me because most matter is inanimate and doesn't make choices. It doesn't have a will, but it is resistant to accelerate. So the more mass, the more resistant it is to accelerate. All right, so let's look at some quick kind of mental math calculations using Newton's second law. We have a 2 kilogram object that has a 6 Newton force being applied to the right. Newton's second law tells us the net force is equal to the mass times the acceleration. There's only one force, so that is the net force, and the mass is 2 kilograms. So if we divide 6 newtons by 2 kilograms, the acceleration would be positive 3 meters per second squared. Although with forces, while we do want to use positives and negatives to think through the math, generally speaking, it's better if you actually give a direction in words, because now that we're working in multiple dimensions and multiple directions, if you just say positive, that could mean right, it could mean up, could mean forward, or we could redefine it to mean something else. So while it's important to use the signs in the math to make sure you're setting it up correctly, the answer is probably clearer if you just use words. So 3 meters per second squared to the right. In the second scenario, still a 2 kilogram object, but now we got some kind of tug of war going. Something's pulling it to the right with 6 newtons. Something else is pulling it back to the left with 7 newtons. So the net force is going to be positive 6 plus negative 7, or 6 minus 7, or 1 newton to the left. So however you want to think through that, the net force is 1 newton to the left. And then if we divide that 1 newton to the left by 2 kilogram mass, the acceleration is 0.5 meters per second squared to the left. Since the force to the left is greater, the net force to the left, or sorry, the net force will be to the left, and therefore the acceleration will also be to the left. And then finally, one that has 2-dimensional forces, you have to break apart the horizontal and vertical, separate those. So horizontally, there's 6 newtons to the right and 6 newtons to the left. So horizontally, they cancel. But vertically, there's only 10 newtons upward, meaning that would be the net force. The horizontal ones cancel, but the vertical one, there is apparently no other vertical force canceling that. This is another one where a student might say, well, wait a minute, there has to be a vertical force. What about gravity? So again, they may be coming up with a strange scenario where maybe they're in the space station. So because they're in constant state of free fall, it's apparent weightlessness. We'll learn more about that after Christmas, but don't add anything. If they say these are the forces, don't say, well, you didn't add gravity and you have to think about gravity, because they could come up with a scenario where they don't. So if they give you a scenario and then ask you to evaluate the forces, then you should think about gravity. But if they say these are the forces, don't add something to it. Okay, so net force is 10 newtons, mass is 20 kilograms. So again, the acceleration will be 0.5 meters per second squared. Since the net force is upward, the acceleration would also be upward. Questions?
If they say,
yeah, go ahead, Jackie.
If they say something about weight, we add gravity, right?
Correct. But that would be usually if they have something like that, they wouldn't do the free body diagram for you. they would tell you a scenario and you would have to come up with the fact that weight would be impactful in that scenario. But if they just give you a diagram with forces labeled on it, unless the question specifically says that you should consider other forces, you should not. You should just leave what they have alone and just focus on that. That isn't typically how they ask many questions, but just to make sure you understand, don't add something that's not there unless in the wording of the question they say you should. All right, here is an example of an object that is being pulled down by gravity. And so we think about that gravitational force field. If this scenario was given where an object is falling and lands in a table, then we could think about the weight of the object being pulled down by the gravitational force field of the Earth. And we know that once it lands on the table, it quit falling. So there has to be an upward force balancing that out. We call that the normal force. Thinking about weight, we can recognize that, yes, the net force is mass times acceleration. If it only has weight when it's in free fall, if there's no air resistance and no normal force, we could find the weight by taking mass times acceleration due to gravity. And so Fg is the force of gravity, or the weight of the object. Mg, that little g, is the acceleration due to gravity. So that's the 9.8 meters per second squared down. So we can always find the weight pretty easily. And some books actually say weight equals mg instead of F sub g. I don't usually write it that way because then typically students want to abbreviate that to a W. And in physics, W stands for work, something we're going to learn next semester. And so then it starts getting confusing because you could have work equals mgh. And if you're meaning weight, then it can be really confusing. So I tend to try to not use W for weight. I either use the whole word or just keep it FG. And in fact, I would say 99.9% of the time, I'm just going to keep it FG. Now, if an object is sitting on the table, then it isn't accelerating, it's just sitting still. The acceleration is 0, therefore the net force must be 0. If the net force is 0, there has to be something going in the opposite direction of the weight. And it must be equal in magnitude, but opposite in direction from the ball's weight. We call it the normal force, and the normal force is always perpendicular to the surface, same meaning in math, normal meaning perpendicular. And it's pushing up to keep the ball from falling down. It's got a supporting force to keep the ball from falling further towards the center of the Earth. This normal force, like we said, is always perpendicular to the surface. And it's the reason we use tables and chairs and such. If I want my calculator to not fall to the ground, I put it on the table. The table supplies a normal force. If I don't want to sit on the ground, I sit on a chair. The chair provides the normal force to keep me from continuing to fall. Questions on weight versus normal force?
This goes to the positive physics assignment that's due today, but there's one with a skateboarder and it goes like in a circle. And I was just kind of confused because I watched one of the videos and it talked about like what to do if the skateboarder is at the top of the circle, but not to do if he's at the side. And I was just kind of confused how that would work with normal force. Yeah.
When we're done during the work time, if you can show me that question, I can talk it through. Okay. I don't remember there one being in this unit, but I just must have forgotten that. That's sounds like they're trying to get you to start to think about some centripetal motion, which is actually the part that I eliminated from the final because we won't get to it till next semester. So without seeing the question directly, I'm not sure exactly how to address it, but we can look at it afterwards and I can help you out.
Okay.
Anything else? All right. A common type of problem that they ask is elevator problems. In fact, I think there's even some elevator problems on the Unit 5. Depending on which questions your assessment drew up, you might see an elevator problem. In this scenario, the elevator is the gray box. The object is the yellow ball. The object has a mass of 2 kilograms. And it says it's moving at a constant upward velocity. If the velocity is constant, the acceleration is 0. If the acceleration is 0, the net force is 0. That doesn't mean there aren't any forces. It just means that whatever forces exist cancel each other. They're equal and opposite. So the weight would just be m times g. And you can see here, they're using -10 instead of -9.8. Side comment, On positive physics, if you haven't noticed that fine print at the bottom of the assessment pages and the work pages, it says you need to use 9.81 and you need to leave your answers to 3 sig figs. So make sure you notice that little fine print as you're completing both the Unit 5 assessment and then later in a couple weeks your exam. But here, they're just using 10. And when you do your College Board exam in May, -10 is fine. And on tests that I give, not on the website, -10 is fine. But positive physics wants you to use -9.81, and it says that on the bottom of the screen. Here, though, it's -20 newtons down because of the weight of the object. And so since it has no acceleration, the upward normal force must also be 20 newtons, just equal to and opposite to the weight force. So that would be a moving at constant velocity. It would be the same if it was at rest, right? If the elevator was at rest, this would be the same picture and the values would be the same. What oftentimes students get confused by is, okay, I'm going upwards, so I must be accelerating. If I'm accelerating, then the normal force must be different. But if you're going upward at a constant velocity, you are not accelerating. And if you think about how it feels on an elevator, right when it starts to rise, you do feel the acceleration. You feel kind of being pressed into the floor. But then after it goes for a while, if you're going several floors, then you don't feel that pressure anymore. It's not because you got used to it. It's because the floor accelerated you. Now you're moving at the same speed as the elevator. And so you are not moving at an accelerated rate. You're just going at the constant velocity of the elevator. Then you feel a change again when the elevator starts to slow down. You feel lighter. You feel like you're kind of leaving the floor a little bit because it is decelerating. It's slowing down. It has a negative acceleration. But your body wants to keep going because of your inertia and your momentum. And so when it starts to slow down and when it starts to speed up, then you feel an acceleration. But in the middle, when it's going at a constant velocity, there is no acceleration. That's when you just feel normal. If you stood on a bathroom scale in an elevator, if you have an opportunity to do this, you could try it. When it first starts to go, it'll read as if you're heavier than you really are. You'll see this needle go up because the floor is having to push against you to accelerate you, which gives you a larger apparent weight. Apparent weight is just normal force, really. And then when it starts to slow down, you'll look lighter. The needle will drop a little bit because your body wants to keep going, but the elevator's slowing down. In the middle, when it's going at constant velocity, it'll just be your normal weight. So it's interesting if you ever have the opportunity to do that. I don't know when you'll be carrying around a bathroom scale and riding an elevator, but if you live in an apartment complex or something, or you have an opportunity to go to a place like that, take a scale, try it out. And you can actually literally see the needle change when it starts to rise and stops rising.
So like your own inertia is what causes it to happen? Is that what it is?
Yeah, because we have inertia, our mass wants to resist changes in motion. So if at the beginning we want to stay at rest, but the elevator pushes us. And so that acceleration goes against our inertia and will make it look like we weigh more than we do. And then at the end, our body's in motion. And because of our inertia, it wants to stay in motion. But the elevator quits pushing us along. And so it starts falling out from under us, so to speak. And so we end up feeling that, that lighter weight and see the lighter value on the scale for that little bit of time when it's slowing down and we haven't quite yet slowed down. All right, so in this case, the elevator's acceleration is 0. Therefore, the net force on the ball is 0 because it's constant velocity. And therefore, the net force and the weight of the object have to add up to 0 as vectors. One's up, one's down, so they have opposite signs. So they add up to 0. Now, the harder scenario, although sometimes this one could be hard just because it's confusing that you're moving and it still has a net force of 0. That's where sometimes you'll get tripped up. But mathematically, the harder one is when you do have an acceleration. Always the normal force is just the upwards push of the floor. In this case, when you're both going at the same velocity, it makes your weight be constant and doesn't seem to be changing. But when it starts to accelerate you, that's when you're going to have an apparent heavier weight on the scale. So in this case, we still have the gray elevator, we still have the 2 kilogram object. The weight of the object won't change, the actual weight. But the apparent weight, what it looks like on the scale, will actually be the normal force having to increase to accelerate the object upward. So in order to make that object accelerate and not stay at rest, the normal force has to be greater than the weight force to cause that acceleration. In this case, they're saying the acceleration is 4 meters per second squared, so actually telling us the value. So to figure out what the normal force is, we know it has to be greater than 20. Otherwise, it wouldn't accelerate. But we can figure out exactly how much it is. How much greater than 20 is it? Well, we know the net force is just mass times acceleration. And we know the net force is also the sum of those two parts, the weight and the normal force. We know the weight will be positive. We know the normal force will be negative because it's downward due to gravity. And normal is upward. We know that the weight force can be calculated using mg. And when you add a negative, that's just subtracting. So we would say the normal force minus the 20 newtons of weight equals 8 newtons of actual net force. And if we solve for the normal force by adding 20 newtons to both sides, the normal force would have to be 28 newtons in the upward direction to cause this acceleration. Questions? Now, one thing that I do mathematically that's slightly different than your textbook, in this first line here under the Newton's second law, it says Fn plus negative Fg equals ma. I don't usually put that negative there because what I've seen students often do, they'll put the negative there and then they'll also put it down here on the 10. And so you're basically putting the negative impact in twice. So the way I would do it if it were me writing this on my own paper, I would not put negative Fg. I would just say Fn plus Fg. And then I would not put Fn plus negative mg. I would just put Fn plus mg. And I would just keep it as addition all the way down. And then I would make my negative 10 where the negative comes in. That just is, for me, less likely for me to accidentally impact or put the negative in 2 times and therefore negate it. This is how the book teaches it. It works fine. You just have to recognize that you don't put the negative on the 10 again because you've already accounted for that negative direction up here in the setup. Okay, so just make sure you don't account for it twice. And I prefer to just account for it by putting it on the 10 and making everything addition. There's no right or wrong way, just different options. Any questions on that one? All right, we'll keep moving. Real quick, we're just going to wrap up Newton's first and third law with a quick summary. So Newton's first law, an object at rest stays at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless a net external force is exerted upon the object. So you should have a definition similar to this in your notes already. It's probably one that you could sort of quote in your own words. I'm sure you've heard it multiple times in your life in different science classes. And then another way to say it, an object will have constant velocity except when a net external force is exerted on that object, in which case that object will accelerate. So 2 different ways to say the same thing. One way sounds much more traditional and textbook. The other way is more common language, but equally accurate. So that is Newton's first law, just a quick reminder. We often call Newton's first law the law of inertia because this is really what inertia is, the tendency to stay at rest or to stay in motion without some external net force being applied. Quick review on free body diagrams. This is like a barbell or a dumbbell or something sitting on a slope. And so if we drew just a force diagram and tried to think about all the forces, there would be friction between the 2 parts that touch the ground and the ground. There would be the weight of each of the parts on the ends and the bar itself. There would be the normal force on the 2 surfaces that are in contact. So you got all kinds of forces. It's not really hard to think it through, but then it's kind of complicated if you're trying to think through the math. That's why we use free body diagrams. Free body diagrams let us simplify complicated scenarios like this by, instead of saying, hey, here's the barbell or dumbbell and all these different forces, let's just make the dumbbell a dot. We can do that. We're not cheating. We're actually just simplifying the scenario. So in this case, we would replace that picture of the dumbbell with its shape by a dot. And that is the object now. right? Then we draw all the forces exerted on that dot. So instead of having to draw all three of those different weight parts that factor in, we just say, well, the weight is down. And instead of the two normal forces at the surface, we just say, well, there is a normal force. And instead of the two different friction forces, we just say, well, there is a friction force. We don't have to separate it into all the different parts. We can think about it as just one object where the table or the ramp is providing a normal force and the surface is creating friction and the Earth's gravitational pull is giving it weight. And you can also notice here, they've tilted the axis. Does anybody remember why tilting the axis is helpful or can be helpful?
Isn't it because otherwise, sorry.
Go ahead, Jenny.
Oh, isn't it because if you do like gravity on the axis, then you would have two tilted for friction and the natural one?
Good. So right now, the normal force is on the y, so it has no components. The friction force is on the x, so it has no components. So we only have to do trig with the weight, the FG. If we put the x and y normal, traditional, the FG wouldn't have components, but the friction and the normal force both would. So that's why we can just simplify it. It's not right or wrong to do it one way. It's just easier to tilt it and limit how much trig you have to do. And then another couple quick comments to summarize this. Don't draw the components of the vectors as forces. It's fine to draw them on there, but don't draw them as arrows. If it's an arrow, then we're assuming it's a force. Draw them as dotted lines. I would draw them on there, but not as forces. And in fact, on the College Board exam, if we take a traditional one on paper at the end of this year, it says on some questions, draw a free body diagram, do not include components. So what I would encourage you in those situations is on your answer sheet, draw it just like they said, on scrap paper, draw your components so you can do the trig, okay? But we shouldn't draw the components as vectors. They're just the parts of a vector. And then all the vectors have to start at the dot and then they all need to be labeled. In this case, normal, friction, and weight. Questions about free body diagrams? All right, last one, Newton's third law. If object A exerts a force on object B exerts a force on A, they have the same magnitude but opposite directions. So a couple of examples of this, we've mentioned a couple earlier, but if we have someone pulling on this green scale, which is attached to a red scale, which is attached to the wall, you actually have four objects here, the person, the green scale, the red scale, and the wall. With Newton's third law, we have to limit ourselves to two things at a time. So one force pair would be the person and the green scale. The person pulls the green scale pulls back on the person. Another force pair would be between the green and the red. The green scale pulls on the red scale pulls on the green. And another force pair would be between the red and the wall. The wall pulls on the scale pulls on the wall. So whenever we're dealing with Newton's third law and trying to think about force pairs, we have to limit ourselves to two objects. When we're doing a free body diagram, we narrow it down to just one object. And we don't really think about the force pairs then, we just think about the forces on that single object. But if it's helpful to think about the Newton's third law pairs to answer some other kind of a question, we have to make sure we're only thinking about two objects at a time. So we could not have a force pair between the person and the wall because the person is not exerting a force directly on the wall. Questions about that? All right, the last scenario, if we had a person pulling on a rope and then the rope was attached to a cabinet, one force pair would be the person and the rope. Another force pair would be the rope and the cabinet. The person doesn't have a force pair with the cabinet because the person isn't touching the cabinet. Now, the amount of tension in the rope would be the same in both cases, but when we think about force pairs, we got to limit ourselves to just two things. And in this, there's at least three things we could talk about. All right, that is it for today. So just wanted to review, add a few little layers of depth on certain topics, but mainly just review a lot. Thursday, we're going to continue to dig into more complicated problems, things like this. This is what we're going to start with on Tuesday, is trying to figure out what if we've got a pulley and objects going in different directions and how do we figure out that? So we're going to start with that and we're begin to look at more and more complicated scenarios. So that's what's coming next time. For today, if you have questions, feel free to hang around. I'd be glad to answer them. If not, you've got the rest of the class time just to work on either Positive Physics Unit 5 assessment, getting that turned in, or you can go ahead and start working on getting your exam preparation started. So otherwise, if you have questions, stick around. Otherwise, you're dismissed, and I'll see you next time.
All right. Thank you, Mr. Webb.
you.
You're welcome.
Have a good day.
Thank you, Mr. Webb.
You too.